The title of this talk is Fossil Fuels and the Fate of the Industrial Civilization. I will begin by recounting how the last 200 years have been powered and by which fuels. Oil is the first of the fossil fuels that will go into decline. And as it's well known, all non-renewable energy resources or resources in general have their growth phase and the decline phase along roughly a bell-shaped curve. Then I'll try to develop a methodology or model on how to predict future oil production. I'll discuss the reserves and discoveries, production, consumption, imports and exports across the world, then tie this all with population growth and its possible decline, and have some closing thoughts. Now, this graph, the data for which comes from the website Our World in Data, shows the growth part of the bell-shaped curve for the global direct primary energy consumption. If you look at the right edge of the curve, you can see coal, oil, and natural gas to be the main components. They comprise of 96% of the total. At the bottom, you have traditional biomass at 7%. And then if you go to the left end of the curve, you see that in year 1800, we were totally on biomass. Now, coal began to be used as a result of the invention of the steam engine, and it took 40 years for it to increase in consumption from 1% to 10%. So at the end, we only had biomass and coal. Then the automobile was invented in the early 1900s, and the oil entered the picture because oil is refined to motor fuels, and its consumption grew quite rapidly. It only took 30 years for it to rise from 1% to 10%. So now we have three: biomass, coal, and oil. Now, next on the graph, you see the natural gas being exploited. Now, it took longer, about 40 years for it to rise, or 50 years rather, for it to rise from 1% to 10%. Now, no other primary energy source has provided more than 10% of the total. In fact, none of them have other ones have even exceeded 5% today. Now, notice that nuclear, we have been at it since about 1965 or so, and it has not exceeded this number. And hydropower, we have been at it for much longer, and it also has fallen short of this threshold. Now, I have chosen 1960 as a reference year here for the reason that I was 17 years old at the time. And from 1960 to 2020, that's a span of 60 years. And many of the students, the younger members of this audience, are 17 years today. So if we go further in another 60 years, we are 2080. And I'm quite confident to tell you that we're going to enter the decline phase of the direct primary energy consumption. So this period of 60 years of my life, professional life, and the next 60 years of your professional life spans the era of 120 years of the industrial civilization, which I claim will have entered into the decline phase long before 2080. Now, the percentage increase of primary energy consumption has increased on the average 2.3% a year. And if you look at the total numbers, they amount now to 160,000 terawatt hours per year, which is about 18 terawatts continuous power in the society. Now, these numbers in more detail are shown here. Notice in 1960, we depended on fossil fuels at 74.3% of our needs. And this has grown to 86%. And note that oil has increased nearly fivefold. Oil has fivefold, yes. Coal nearly fourfold, and natural gas nearly ninefold. Biomass was 21.3% still in 1960. Today, despite of having grown slightly, it has dropped to 7%. In 1960, we had no nuclear, wind or solar or other forms. Hydro was 4.3%, and despite having more than doubled until today, it has dropped to 2.7% of the total. Now, the more modern forms of energy, the wind farms, which we see, are now 1%, and solar is 0.4%. And the other include things like modern biofuels, ethanol, palm oil, and rapeseed oil, as well as geothermal, and a small amount of tidal power. I think there are only 5 tidal power stations in the world. They are all quite small. Now, when you examine the table on the right side, the present consumption, you notice how small nuclear, hydro, and all the other forms are. To be sure, there are countries such as France who get 36% of their primary energy from nuclear. Brazil gets about 31% of its energy from hydro. And a country like South Africa gets 71% of its energy from burning coal. I am sure that Saudi Arabia gets most of its energy from natural gas and oil. So these numbers vary from country to country, and these, what I have here, are the averages for the entire world. Now let's move to discuss electricity production in the world. Notice again that coal, gas, and to less extent oil constitute about 63% of the primary production, or electricity production rather. Okay, now the total is about 26,000 terawatt hours per year. And if you compare that to the previous 160,000 terawatt hours per year for total primary production, this is only 16% of the total. Now you might wonder why it is so low, because we certainly use a lot of oil and coal and natural gas to generate electricity. Well, the reason is that the coal and gas is consumed in thermal power plants, and we know that their efficiency limit is the so-called Carnot efficiency. And in fact, the average efficiency of this plant is about 40%. So 60% of that energy goes out as waste heat. Now, when it comes to nuclear energy, we don't worry about the waste heat for the simple reason that there are no other uses for the nuclear fuels. Okay, this is in contrast to oil and gas in particular. Gas is the used to heat houses in the northern hemisphere, and then the wetter parts of the natural gas goes into cooking fuel in the south. Also, it is the main ingredient of fertilizer production throughout the world. Coal, okay, about 90% of it goes to electricity production, But the last 10% is used in industrial processes such as metallurgical coal for steel making and a very large industry in making cement to build the infrastructure in the world. Okay, so we just measure the electricity coming out of a nuclear power plant, and that is assigned to the primary production part of nuclear energy. Now, the same is true for hydropower, solar, and wind. We don't worry about the losses. Hydropower, in fact, is quite efficient, but the wind and solar, you don't try to take all the kinetic energy out of the wind. The flow would stop going through the wind turbine. And solar power cells are about 13% efficient. Now, the wind power is, there's a Betz limit, which is about 59%. That's a theoretical limit on the efficiency of wind. Now, there's another aspect, though. When you, the wind doesn't blow all the time, and you cannot collect solar energy at night. So there's something called a capacity factor, which is the amount of electricity generated by wind and solar divided by their nameplate capacity. This turns out to be about 23% for both wind and for solar energy. Now, you read articles that the world has increased the capacity by a certain amount in solar and wind this year or last. And when you read those things, you have to remember that about a quarter of it only goes into actually delivered as electricity. Similarly, you might read that solar energy has provided 100% of the electricity in some country or another. Here you have to remember that this probably took place for 1 hour at the best possible day of the year at the optimum hour of the day. Well, these trade publications like to spin the story this way as they are trying to boost the use of renewable energies. So we will forgive them. Now, I want to next talk about the growth and decline of oil production. There are basically two methods of doing it. One is to do what is called a bottoms-up analysis. It consists of getting hold of the database of about 50,000 oil fields in the world. It was done by a group at Uppsala University under the direction of Professor Kjell Aleklet, and they have produced a number of good reports from there. The PhD students, Frederick Robelius and Michael Herc, produced these reports, as well as a number of technical publications in the peer-reviewed journals. What they found was that the largest 25 fields provide a quarter of world's oil production. And then when you extend it to 500 largest fields, they provide a little over 50% of the world's oil production. Well, 500 fields out of the 50,000, that is 1%. So you can see that the oil production in the world is concentrated greatly into the very large fields, which exist mostly in the Persian Gulf region. Although there are some other ones, for example, have been in Russia and China and even the Gulf of Mexico. Okay, now, the way in which these large fields are brought into production is after the discovery, they start building the infrastructure to process the oil, and then they ramp up the oil production to some level. This level is decided upon by the size of the estimated reserve. And then you try to keep this production at this plateau for a very long time, say 20, 30, 40, even 50 years. Okay. Then the analysis shows that, okay, you can determine how much of the field was depleted when it entered a decline. And after the decline, you can determine the rate of decline. So by this method, this group in Uppsala came up with the result that the world's oil will peak by 2018. Okay, now I will use a different method to model this thing. It was pioneered by the American geophysicist M. King Hubbert, who already in 1950 started to draw these bell-shaped curves by hand and counted the area under the curve by adding the squares under it. But by 1982, he had latched onto a mathematical method or mathematical model to do the same. I will follow his approach here, which is based on this logistic equation. It's given on the top left corner of the slide. Q, capital Q, is the dependent variable. It's a cumulative production. That is to say, you sum up the yearly production from the beginning until today, and that's the cumulative. If you take dq to be the yearly increment of production and dt to be 1 year, the ratio or the derivative dq dt is the yearly production. So the left-hand side of this equation represents the yearly production. Now, the right-hand side is some function of the cumulative. And there are two parameters in there, A and Q0. Now, what are these parameters? Now, first note that at the very beginning of oil production, obviously the yearly production is 0, and so is the cumulative. So that fits into this data or the equation. Then at the end of the oil production, the yearly production drops to 0 again. Well, that is true when Q is equal to Q0. So Q0 then represents the ultimate production, that is how much has been produced from the beginning of oil industry to the very end. Then there's also this parameter A, and the way to figure what that means is that to note that at the very beginning of oil production, Q is much more than Q0, so you can drop the second term and you get a equation which shows exponential increase growth with the initial growth rate of A. Now, if you recast this equation in terms of the remaining oil, which is Q0 minus Q, again at you get the same equation with the minus sign, and again at the end of the oil production, QR is much smaller than Q0. You can drop that term, and what you get left is an expression which shows an exponential decline. So the A is either the initial growth rate or the final decay rate. Okay, now we have a physical meaning for all the terms and the parameters. Now you can get more out of this equation before solving it. Namely, if you look at the right side, it's a parabola. And plotted against Q, this parabola crosses the axis at Q equal to 0, as well as Q equal to Q0. And such a parabola has its maximum at the midpoint, so at Q equal to 1/2 Q0. So if you substitute that to the right-hand side, what you get is the yearly maximum production given by the formula AQ0 divided by 4. So that's a handy formula, simple to use if you know what A and Q0 are. So the next task is to see how to get approximations for A and Q0. Well, it's done the following way. You divide both sides of this equation by capital Q. So the left-hand side is now the yearly production divided by the cumulative. And since you have been collecting all this data every year, you have the values for the yearly production, the cumulative at any one year. So you can plot it on the ordinate. On the abscissa, you plot the cumulative. Now, you can see that this becomes a straight line, which crosses the abscissa at Q equal to Q0 and the ordinate at the value of A. Okay, so therefore you can get these two parameters estimated from this kind of plot, and I have put some data which happens to be, I mean, I designed it that way to fall on this line to illustrate how to use it. Now let's next solve this equation. Separate the variables, expand by partial fractions, integrate both sides, and then collect terms and simplify the result as much as possible, and you come up with this expression. Here Tp serves as an integration constant. Note that when the year t is equal to Tp, hyperbolic tangent is 0, and you get that Q is equal to 1/2 Q0. Well, I just said that that corresponds to the maximum production year. So Tp represents the maximum year of maximum production. I like the second part of this expression better because it shows the anti-symmetry of this function about the midpoint. Now, this function is called the sigmoidal function, and it is typical of all non-renewable resource exploitation. Now, if you differentiate it, you get the yearly production. And again, the second part shows that when T is equal to the peak production year, it reduces to AQ0/4, which we already established by other method. It also shows that only the distance from the peak is important. It doesn't matter if you are below the peak or after it, as long as you're same distance away, which means basically that this curve is symmetric. You note that I had chosen the range from 1960 to 2080 and the peak to be at 2020. Now, what happens when you put the actual data into this kind of a plot? Well, first to note is that in the early phases, if you try to draw a straight line, you get a quite a much steeper slope than you would get today. That means that the Q0 is much smaller at that time than it would be today. So you're predicting the peak year to be much earlier than today. The other thing to note is that this data falls kind of like in a concave curve until it starts to settle down into a linear fit. Okay, when I was in India in year 2005, I was doing these kind of calculations, and obviously I didn't have the last 15 years worth of data at the time. And I drew that dotted line in there, and I got that the Q0 was 2300, whereas today is about 2800. Now, I tried to predict the peak year by, let's say, limiting the range of the data from anywhere from 10 years up to 25 years. Now, if you include 25 years of data at that time, you're including data from higher up on the curve, and you're going to get a steeper slope. So by this method, I predicted that the 2014 would be the peak year. So that was going to be 9 years in the future. Okay. So now, if I do this calculation today, this is the kind of a plot I get. On the horizontal axis, there's a year at which the prediction is made. In the vertical axis is the predicted peak year. And the black line shows how it has drifted forward in time. Now, notice that it was quite constant there about 2016 for nearly 10 years. But now it has started to increase again. And of course, the last 2 years were the pandemic years, but it now has crossed this to the right-hand side of this diagonal, which means that the peak year is past. Okay. Now I also have this ultimate, and it shows on the right side, and it shows how it has increased over the years. Now, I want to discuss a little bit more about why this sudden rise or sustained rise over the last 15 years or so has taken place. Because if you plot the yearly production, You can see the graph, which looks like this. You see the 2018 as the peak year, 2019 a little bit less, but then the COVID came and the oil consumption and production dropped quite a bit. Now, I also then here's the cumulative production. It asymptotes to the 2800, and then I also plotted the world and world excluding the USA. And if you look at the lower graph where United States is excluded, you notice that the blue circles there at the peak, they don't grow very much from year to year. In contrast to when the United States is included, you have a very strong growth from 2010 on. Well, that is the result of the so-called fracking technology introduced in the United States over the last 10 years or so. And the way it's done is that you drill into vertically first, and then you turn the drill bit horizontally, and you drill these laterals, as they are called, and then you charge it with water with sand and blast it through a perforated pipe to fracture the strata surrounding this wellbore. That's where the word fracking comes from. Then the oil flows from the strata into the pipe, and it is retrieved from there. Now, you cannot drill these laterals too close to each other because they interfere with each other, and you don't get as much out of one well as you would if they are further apart. So the so-called well productivity would go down. Also, you cannot drill these laterals too long because they start interfering with some other wells which are nearby. Okay, now this kind of oil exists. The main region is the Permian Basin in Texas, and it extends to New Mexico. There's another one in North Dakota, the Bakken Formation, Niobrara in Colorado. There are a couple of old ones in Texas, Austin Chalk and Eagle Ford. And then there's a large region in western Pennsylvania, the Marcellus Shale, but that produces mainly natural gas. Okay. So now I also plotted the world's total liquid production, and it's shown here. You can separate oil into 4 different categories. One is the very heavy oil, then there's kind of regular oil, then there are reservoirs which are called gas condensate reservoirs. The largest one is in the Persian Gulf, shared jointly with Iran. It's called the South Pars Field in Iran, and Qatar is called the North Field there. And in those reservoirs, the hydrocarbons are such that they are a little heavier than in natural gas, which is basically methane, but not as heavy as in regular oil. So when it comes out of the reservoir, most of it condenses out as liquid. So you can put it in with a liquid stream. And typically, we are interested in crude and condensate only because those are the things which are more important in producing these motor fuels. Now, when you go to produce natural gas, when you collect the natural gas and you transport it into a natural gas plant, there the pressure is so low, sufficiently low, that there's more condensate coming out of the natural gas. This is, of course, very light stuff, and it actually is used mostly in the petrochemical industry, making plastics and so forth. But nevertheless, if you add it to the crude and condensate, you get an increase of about 20% for the total liquids. And this is what the world's reporting agencies provide. They provide data for crude and condensate as well as total liquids. They are the International Energy Agency in Paris, United States Energy Information Agency, as well as the British Petroleum Statistical Review of World's Energy. Okay, so looks like it's about 100 million barrels a day for the world we are about the peak. Notice that the peak here has moved to 2025 for total liquids, and ultimate has increased to 3,600. We have used so far about 1,600 billion barrels of this oil and liquids. Now let's talk about reserves and discovery. This is a graph of world's oil reserves. And when you casually look at it, and you see that in 1980, we had about 700 billion barrels, and today we have 1,700. So you say, well, the reserves are growing. What's the difficulty? There doesn't seem to be any end in sight here. But there are a couple of things to notice first, or to remark on this thing. First of all is that the publication Oil and Gas Journal sends out an inquiry into all the countries in the world who are producing oil, and if they don't get a response, they just include the last year's reserves. And in many countries where they get a response, it shows that the reserves were the same as the year before, despite the fact that lots of oil was produced in that country. So this data is not that accurate because of this reporting requirement is not mandatory, and these reserves are never audited. Now, there's another aspect, is the so-called Opec Quarter War, which took place between 1980 and 1990. And what happened at that time was that the OPEC organization changed the way in which they allocate the production quota to the member countries. So what they did was they made the size of the reserves as a component in their consideration of how much the member country could produce. So the natural result of this was that everybody increased their reserves. And the estimates are that there were about 300 billion barrels of extra oil made by this, what you might call an accounting trick. Now, some of it was probably justified. And so the amount of paper barrels in here is probably only about 200,000 or 200 billion barrels. Now, another thing happened later is that these reporting agencies, as well as Oil and Gas Journal, decided to start including the heavy oil from Venezuela and the tar sands of Canada into the reserve numbers. You can see how much came from, it was increased in Canada and Venezuela. So together about 360 billion barrels. Now, as I mentioned earlier, this heavy oil is fairly slow to produce. To be sure, Canada has been at it for quite a long time, and it's already producing so much that it is one of the main exporting countries in the world. Venezuela, on the other hand, has been, as a result of the economic difficulties there, the production has gone down, and I don't know when they're going to manage to revive the economy. Now, there's something different, positive still here, is that as petroleum geologists and engineers have gained experience in how they produce from a given reservoir, so the technical ability is increasing, and they're able to get more oil from the reservoir than originally thought. So this difference is called reserve growth, and it's actually quite substantial and explains partly why these reserve numbers have gone up. Okay, but nevertheless, if we now look at the discoveries over a large span of time, the largest discovery was made in 1948, the Gawar field in Saudi Arabia. The peak discovery was around 1965, and today we don't discover very much at all anymore. Now, again, the Ghawar field, as it was the largest field, the Saudi Aramco decided to produce at a certain steady rate, this plateau production. It was at 5 million barrels a day. And it has been producing this 5 million for a very long time. Now, last year, Saudi Arabia decided that they wanted to list the oil company Saudi Aramco at the world's stock markets. And as a result of that, they had to open their books to inspection by outside inspectors. And it revealed that the Ghawar production had dropped to 3.5 million barrels. So that's a large drop from the 5 million to 3.5. In fact, I think the only two other oil fields in the world which produce over 1 million barrels, the Greater Burgan field in Kuwait and the Rumaila field in Iraq. Now, it turns out that the Saudi Arabia did not allow the inspectors to do such a thorough job in inspecting these books, and the result was that the stock got listed only in Saudi Arabia's own stock exchange. Now, just a week or so ago, I saw a press report that Saudi Aramco was going to issue a secondary set of shares at the tune of 50 billion and hope to list them both in Singapore and London. Well, the outcome is still uncertain. Now, the last year, we discovered 4.7 billion barrels of oil, and we use oil at the rate of 1 billion barrels every 12 days. So 5 billion barrels is a 2-month supply, 60 days. So that is the rest of the year, we have to get the oil from these large aging reservoirs, many of which are already in the decline phase. So now let's return to discussing production, exports, and imports and domestic consumption around the world. And here are the various continents: North America and South and Central America. You note that the green line, it's negative, it's imports, positive, it's exports, and both on the Western Hemisphere, they seem to be nearly at zero. So no help from the Western Hemisphere, the rest of the world. Then when you go to Africa, you see that the peak year was 2007, and it has been in decline. The large countries, such as oil-producing countries in the West Africa, such as Nigeria and Angola, are in decline, and so are the Northern African countries of Libya and Algeria. The smaller ones in West Africa, Gabon, Equatorial Guinea, are also in decline. And in North Africa, Egypt is producing at the rate nearly as the same as they are consuming. Well, then we come to, and notice, by the way, also the rapid rise in the domestic consumption in both Africa and South and Central America. North Africa, the scale is a factor of 4 different there, so you have to adjust the slope accordingly. Now, when we come to Europe, you can see that they've been importing oil for a very long time. You see the hump in the production from the North Sea, but their consumption has been fairly flat for a very long time as well. When we come to Middle East, you see that there has been robust growth from 1985. The exports have been not nearly as high because domestic consumption has again increased a lot. Incidentally, Saudi Arabia has been exporting at about 8 million barrels a day since 1990, so for the last 30 years. It has not varied a lot from that 8 million barrels each year. Then we come to Eurasia, or the former Soviet Union, and you can see the collapse of the Soviet Union and the subsequent rise in the oil production. Russia produces today about 10 million barrels a day, and the rest is from Kazakhstan and Azerbaijan mainly. The consumption has not increased that much over the last few years. because the money just doesn't flow to the people for them to spend on new cars and so on. Now, when you come to your part of the world, which is Asia Pacific, note that there's been steady increases in consumption. First part is the industrialization of Japan, then comes South Korea, then comes Taiwan and Southeast Asia, then comes China and India. So now the consumption is approaching 40 million barrels a day, and the imports are approaching 30 million because the production is plateaued and is starting to come down. Now, when you look at the imports for India and China separately and together, you note that how they are increasing. And if I put a quadratic through the data, the combined imports are supposed to reach 20 million barrels a day by 2025. Well, there's an extra 5 million barrels here, and I don't know where that would come from. Now, I also plotted a graph which shows the oil exporting countries. The bottom 5 are the main part of this thing. They include Russia, Saudi Arabia, Iraq, Canada, United Arab Emirates. Then comes the next 5 and so on. And the last 5, between the last two fives, the gap is quite narrow. And in fact, the trend has now turned down. Now I have to still talk about the population trend. And it also, the growth rate of the world's population also goes through this kind of a bell-shaped curve. It peaked in 1970 at 2.1%. And at that time, the increase for the world was 90 million people. It has now dropped to just under 1%. But because we now have 7.9 billion people on this planet, the increase represents 80 million people still. Now, the projection is that we're going to reach something like 11.2 billion by the end of the century. And you note how the rate is dropping over that time. Now, this kind of sigmoidal curve we have seen to be valid for exploitation of non-renewable resources. But these are, now we're applying it to a biological species. And we know that, for example, the cod population in the world's oceans has dropped dramatically because of overfishing. So what you can say that the death rate of the cod is larger than the birth rate. So as a consequence, this annual growth rate has gone negative. And the sigmoidal curve has reached a plateau and then start to drop quite drastically in the case of cod. This is, of course, also possible for humans. And of course, our task is basically to try to reduce its population in a gentle fashion to a value which allows us to live with the traditional biomass and whatever nuclear and hydropower we have left. The trouble with windmills and solar collectors is that they have a life of about 20 years, and then they have to be rebuilt. And we have no idea on how much energy we will have after, let's say, the second rebuild when they are no longer operative. Now, the people who study these kind of things say that we can possibly support about 2 billion people with these traditional biomass and hydropower. Okay. So how to accomplish this decline is the important question for us. Now, the fact that my original claim is that the industrial civilization will necessarily collapse is a consequence of loss of thermodynamics. You can think about the entire humanity as a thermodynamic system that exists at a metastable state as long as it is able to obtain sufficient amounts of energy and raw materials to carry out the things which are needed to keep it at this state. Once these flows begin to slow down, not only in quantity, but also in the resource quality. In energy, that means that the exergy is lower for the fuels are left. There's also this so-called Pareto Principle, which states that the first 80% of some activity takes 20% of the effort, and the last 20% takes 80% of the effort. Applied to this stuff, it says that we have used the best quality oil and gas and coal already, so that this drop in the decline side of the bell-shaped curve can be quite rapid. The hope is that we will have a kind of a catabolic collapse, that is to say, that leads to simplification of all the things we do in this world. So anyway, this question is, how far does this thermodynamic system, the humanity, drop down? And you know, we hope that they, of course, as it goes down far enough, we still have sunlight to grow the biomass which we will need. So we are basically saying we are moving into a pre-industrial state again. Oil is the first fossil fuel to decline. It will influence transportation mainly. Now there's a notion that we have to move to electric cars, and there are great attempts around the world to do this thing. But in my view, this is a very bad idea, because as you have seen, electricity is produced by coal and natural gas, and that will just move their peaks closer because of this increment of electricity going to cars. Now, of course, I'm all for electrifying the public transportation system, but for the rest of it, we should just use our bikes and walk, and certainly stop all this worldwide travel. And this technology which we are using helps greatly in that context. The natural gas peak production will come in about 20 years' time. I've already reviewed on what it's been going to be used. But then there's an important aspect, namely that the natural gas markets tend to be continental. In fact, but now recently there has been large increase in the so-called liquefied natural gas being transported across the oceans. And it's basically now half as much as is done by pipelines. Now, these pipelines crisscross these continents in the United States. You can see the maps of them. And in Europe, Russian gas comes to Europe as well as going to Far East, and because they are part of both Europe and Asia. So this is what's going on. So anyway, because of this continental nature of these gas markets, I foresee localized shortages of natural gas in various parts of the world. And we have already seen that in Europe this year, where the gas prices went up drastically. This is the chart for natural gas, a peak at 2042. And then we come to coal. And coal markets are even more concentrated on the localities where the coal exists. The seaborne coal is only 20% of the total consumed. It comes mainly from Australia, Indonesia, South Africa, and it is exported into Japan, South Korea, Taiwan. Some of it comes to India, and India also gets, of course, some from South Africa. It turns out that the Indonesian coal is not very good quality. And my understanding is that the Indian coal is also mostly lignite. Now, USA and Russia have the largest coal reserves on the last to peak, but that is also expected to be here by 25 years. Anyway, China incredibly consumes and produces and consumes about half of the world's oil production. You can therefore also plot its yearly production curve and consumption curve, and this is what it shows. Now the fit is not very good because it had this hump and then dropped and then increased again. But there's a confirmation to this kind of a graph and study by a group in a Chinese university, and they obviously can read the reports in the original language, and also by a American Chinese professor at University of Utah. And when they do this analysis, they come essentially to the same result. The Chinese group in China, they use a little bit different method, but come up with the same result. Okay, so now the way forward is to contract our economy, contract our consumption. Hopefully it'll sharpen our thinking so we can, when the decline starts, so we can reject false solutions out of hand. And other thing, we hope that the fertility rates keep on dropping sufficiently that the world's population will first stabilize and then reduce. And if the younger cohorts which enter this world are smaller, increasing smaller, then the parents go live with their children and hopefully die of old age rather than by any famine or, God forbid, an all-out war. So I'll leave this you with this statement by the Stoic philosopher Seneca, "Ducunt fata volentem, nolentem trahunt," which says, "Fate favors those who follow her voluntarily, those who don't, she drags along." Thank you very much.